Hi, I'm Zor. Welcome to Unizor Education. I'd like to dedicate this lecture to higher order equations. This is the second lecture, it's a continuation of the previous one, and just a couple of words maybe before that. Why do we really need to solve higher order equations? Well, usually we don't. It's just a challenge, it's an intellectual exercise. Ability to solve higher order equations goes back to history. Obviously, linear equations and quadratic equations were quite simply to solve, and the formulas were known for a very, very long time. So it was really challenging to come up with analogous formulas to solve equations of the third degree, fourth degree, and etc. Well, there were certain successes and certain not that successful attempts to do this. There is a famous formula of Cardano to solve equation of the third degree. So the solutions are expressed as a very large formula where coefficients of this cubical equation, cubical because it's third degree, participate. Now, I don't know if any successful attempt to come up with a formula for equation of the fourth degree was invented. But starting from the fifth degree, there was a famous theorem proven by French mathematician Galois, if I'm not mistaken, that it's not really possible the general equation of the polynomial equation of the fifth degree to express the solutions through this equation as a formula, however complex, where coefficients are involved. That's a very interesting, though negative, result. So, in general, we obviously don't want to use any formulas. So the question is, how can we solve equations of the higher order? Well, there are a few techniques. Sometimes they might work, sometimes they don't work. And I'm going to talk about a couple of techniques, a couple of approaches to solve higher order equations. Again, it's purely intellectual exercise. So if you can find some interesting peculiarity about this or that particular equation to be able to solve it, well, that basically is the purpose of the whole thing of solving these equations. So if you see some problem in the textbook or anywhere else where the higher order polynomial equation participates, most likely they are asking you to find what's specific, not general, about this particular equation, which you can use to find the solutions. And that's exactly what I'm going to talk about. What kind of specific cases exist where you can solve the equation of the higher order, and to recognize these specifics looking at any particular equation is actually the challenge, is actually the problem is all about. Alright, so this is a generalized polynomial equation of the nth degree. So it's polynomial because this is the polynomial, nth degree because the coefficient at x to the nth power, a0, is not equal to 0. So it's a true nth degree polynomial, and it's equal to 0. It means that a0, a1, etc., an are known coefficients, x is an unknown variable, and we have to solve it. And obviously we are not talking about this general case because there is no, generally speaking, especially with n greater than 4, there is no formula which would help you. So you have to approach some specific, what is particular about this particular equation, which can help you to solve the equation, to solve it. All right. So the first thing which comes to mind is the following. Let's assume that this particular equation, this particular polynomial, which I can just for brevity call a polynomial because the coefficients are a0, a1, etc., can be represented as a product of two other polynomials. So a0 x to the n plus etc. plus a n maybe, I'm not talking about every polynomial in general, I'm talking about any particular case where this is possible, to the, let's say, nth degree, multiplied by another polynomial of nth degree. This is supposed to be L, and this is supposed to be N indices. From B0 to BL, from x to the power of L to the x to the zeroth power, same thing here. So, if this is true, now, why am I talking about this? Well, think about it this way. For instance, we have this representation. A polynomial is a product of B polynomial and C polynomial. Well, number first, the very important thing which you can observe is that these two polynomials are of lower degree than n. Why? Here's why. If you will open the parentheses, you will multiply this by this plus this plus this plus this plus this multiplied by this, and this, etc., etc. What is the element in the obtained sum of different little products? What is the element with the higher power? Well, that's obviously the higher power from here and higher power, highest actually, not higher, highest power, from here and from here. So, the whole thing is equal to B0, C0, x to the power of L plus m, and only this coefficient, B0 times C0, is with x to the power of L plus m. Anything else, any other product of elements of this times elements of this, would have a lower degree. This times this would be L plus m minus 1. This plus this would be also L plus m minus 1. So everything else will be lower power. And the only thing which is the highest power is this one, which necessitates that L plus m is equal to n. Right? This is supposed to be equal to this. And B0 times Z0 should be equal to A0. Well, this alone actually tells us that both L and M are less than n. We are not talking about 0 degrees because power 0 means constant. We are not talking about constant. It's a true representation of polynomial as a product of two real polynomial of the power greater than 0, so it's not constants. Okay, so number one, the observation which we made is that the power of any one of those is smaller than n. Well, smaller power means easier to solve, right? Well, at least that's what people think about. The lower the degree of the polynomial, the easier it is to solve, to find the solutions of polynomial equation. Alright, so now let's assume that after we have represented our polynomial, original polynomial, in this way, let's assume that after that we can solve an equation which involves only one of those polynomials. Let's assume we can solve this equation. And there is a solution to this equation. So there is some number whatever the number is, let's say x is equal to p, which if substituted instead of x will turn the whole polynomial into 0. What does it mean? Well, considering this representation, if you will substitute p into this equation, and knowing that this polynomial is equal to product of this, so p is substituted into each of these, and this is equal to 0 because p is a solution of this equation. So what does it mean? It means this is also equal to 0. Since this component is 0, multiplied by whatever it is would be 0, so this is 0. Which means what? It means that the p is also a solution of this original equation. It's the root of the polynomial, as they say. The root means it's the value which transforms polynomial into 0. So, if you can solve a lower power polynomial equation, then its root is also the root of the original equation. So that actually paves the way to at least approach to solve certain, not all of them, but certain higher order polynomial equation. And what's the recipe? Well, first of all, try to represent this polynomial as the product of two polynomials of lower degree. And then try to solve one of these. Maybe it's easier. So, if this is the polynomial of the third degree, for instance, it might be represented as a product of two polynomials, one of the first degree and another of the second degree. This is a linear, this is a quadratic. In both cases, linear equation we can solve and quadratic equation we can solve. So, instead of solving equation of the third degree, if we manage to represent it as a product of two polynomials of the first and the second degree, then we can actually solve the whole problem. We will see all the solutions of the original equation. So this is the first approach. Represent our polynomial as the product of two polynomials of the lower degree and try to solve polynomial equations of lower degree. Okay, fine. Done. Next. Next is a very interesting observation. Let's assume that somehow we have guessed one particular solution to this equation. We found the root of this equation. So this is the root. Doesn't matter how. Maybe somebody told us. Maybe we have just, looked at the equation and realized, okay, this is the solution. Does it help us? Well, the purpose is to find all the solutions, right? Whenever we are talking about quadratic equation, we usually are looking for two solutions. Sometimes it can be 1, sometimes it can be 0, but we are not stopping at finding one particular solution and saying, okay, that's it, the problem is solved. No, we're trying to investigate completely what other solutions might exist. So here is exactly the same problem. And what I'm going to say is that knowing one particular root at least helps us. I'm not saying it solves completely the problem of finding all other roots, but it helps us to find other roots. And here is why. So what I'm going to say is the following. For instance, x equals p is a root of this particular polynomial. What does it mean? Well, it means that a0, p to the n's, plus etc. plus a0 is really equals to 0. So p is a number, and a0 and an and a1 and a2 and etc. and an are all some real numbers, and p is the coefficient. Well, maybe real, maybe complex. I'm not really restricting myself to the real numbers. Complex as well. All right, so let's assume that somehow we know that this is the fact. Now, what I'm stating right now is the following, that the a polynomial, original one, can be represented as a product of x minus p times some kind of a b polynomial of n minus 1th degree. From b0 to bn minus 1, and x to the power of n minus 1 down to x0, which is a constant. So you can always divide the original polynomial by x minus p, where p is the root. And I'm going to prove it, actually. There are certain, a little bit more difficult theorems which I'm leaving without proof, but that's a rare case. I'm trying not to do it too often. But this is something which can be proven, and relatively simply. All right, how can I prove it? Very simply. Let me consider this as existing equation between whatever is known and whatever is unknown. What is known here? Well, coefficients from a0 to an are known. P is, again, a known root of the original equation, which means this is also a known equality. It's not equation, it's equality, because P is some number. Now, x can be anything. So this equation, I presume, if it exists, it must be valid for any x. Anything, any at all. Now, b0, b1, etc., bn minus 1 are not known coefficients. And I'm going to explicitly find these coefficients. How can I do it? Okay, here's how. Let's just multiply this by this. And as a result of this multiplication, I will get on the left side my original a0, x to the n's, etc. And on the right, I will also have some polynomial with x in to a certain power. So x I will multiply by each of those, and then minus p multiplied by each of those. Now, what will be the result of multiplication of x times these? It would be, obviously, b0, x to the n's, right? X to the first degree and x to the n minus first. So when I multiply one by another, my exponents are added together, so it will be n. This is 1, this is n minus 1. Similarly, next one would be n minus 1, etc., and n minus 1. So let's say n minus 2. Before that was x, it was x squared plus bn minus 1 x. That would be if I multiply x by all of these. Now minus p multiplied by all of them. So p multiplied by this would be p b0 x n minus 1 plus p b1 x minus 2 plus etc. Now, the one before that was bn minus 2x, so it would be here. P bn minus 2x minus p bn minus 1. So that's the result of multiplication. Now, I know that this polynomial is supposed to be equal to this polynomial with any, for any x. X is a variable, so if polynomials are equal, their coefficients are supposed to be equal. Which means that the coefficient at x to the nth degree, so let me just wipe out this, we don't need it anymore. Coefficient at x to the power of n is what? In this case, it's A0. And in this case, it's just B0. Now, coefficient at x to the power of n minus 1. This is A1, and this is B1 minus PB0. B1 minus PB0, which is equal to, I know what B0 is already, so it's B1 minus PA0, from which I can derive that B1 is equal to A1 plus PA0. Next, A2, this is the power, this is the coefficient at x to the power n minus 2. N minus 2 is next to this one. It would be B2, which is here, plus PB1. Now, I know what B1 is, so it's B2 plus PA1 plus P squared A0, from which B2 is equal to, minus, I'm sorry, this is supposed to be minus. Sorry. No, I'm sorry. This is plus, this is minus. So this is minus. Okay. So B2 minus PB1. Well, I put minus here, but I didn't really put minuses here. That's my mistake. And that's why I'm kind of confused. This is minus P, so everything should be with a minus sign. So everything here should be with a minus sign, which means whenever I resolve it for B2, it would be A2 plus P A1 plus P squared A0. Well, I hope you see the way how it goes. So, without going into the details and without a rigorous proof by induction, I hope that you will just believe me that any coefficient bi is equal to ai plus pa1 plus p squared. Well, let me just do it differently. Plus p a minus 1 plus p squared n minus 2 plus etc. plus p to the I A0. This is I. Just sequentially doing exactly the same steps which I did before. So this is a generalized expression for BIs. Now, well, great. Basically, I found all my BIs. There is one little detail. Whenever I multiply, let me write it again, x minus p times b0 x to the n minus 1 plus etc. plus bn minus 1. I compared all the coefficients of this product to the corresponding coefficients of the original A polynomial. But what I didn't do, I did not specify the very last one. I specified with x to the n minus 1, x to the n, x to the n minus 1, x to the n minus 2, etc., x to the first degree. And I did not really use this free constant, which is minus b times b n minus 1, which is supposed to be a n's. So this looks like this is yet another equation for bn minus first, because the last one in this row would be bn minus 1 equals to a n minus 1 plus p a n minus 2 plus p square a n minus 3 plus etc. plus p to the n minus 1 a 0. So it looks like I have two different expressions for bn minus 1. And this one shouldn't contradict this. Well, otherwise I'm basically coming up with a contradictory set of equations for bn minus first at least. Now, let me show that this is not a contradiction. If bn minus first is equal to this, then what's important is, don't forget that p is a root of the original equation. Let's multiply minus p by this expression for bn minus 1. What do we have? Well, we have this equation. an equals to minus p a n minus 1 minus p square a n minus 2 minus etc. minus p to the n's a 0. What is this? Well, move everything to the left side and you will see the original equation, which is p to the n's times a0, this is this one, it's on the left, plus a1 p to the n minus 1, etc., plus this one, p a n minus 1 p and plus a n equals to 0. And we know that this is true because p is the root of the original equation. This is our original assumption. If p is the root, then the whole polynomial can be represented in this format. So the fact that p is the root actually is the only significant piece which is required here, and only this makes our system of equations where we derived actually with b first, b second, etc., only this makes it really a true solution. Because if p is not the root of this original polynomial, if this is not an equation of the original high-order polynomial equation, then this is not true. And if this is not true, then this would be a contradictory to equalities, which means there is no solution. So a solution exists with concrete b0, etc., bn minus 1 expressed as this particular set of equations. It exists only in case when p is a true root. That's why we are saying that if p is a root, and we don't know, maybe it doesn't exist, but if it exists, this is very important. If exists, then the original polynomial can be represented in this way. Now, what's good about this? Well, as I was saying, if you represent the polynomial as a product of two other polynomials, these are of a lower degree. And obviously, this polynomial has a root x equals p, which we already know, and this polynomial is of n minus first degree, which is easier to solve than the polynomial of the nth degree. So this is basically the conclusion of this logical steps. Again, if you know somehow that there is a solution of the original polynomial equation x equals p, then the original polynomial can be represented in this way, and these are the way how you derive the coefficients b0, b1, etc. up to bn minus 1. You get the second equation to be solved, which is of lower power, lower degree, and that makes your life easier. which means if you know one root to equation, it allows you to reduce the problem of solving this original equation to find other roots into a easier problem to solve the polynomial equation of the lower degree. All right. That's what guessing the root gives you. Well, how can you guess? Well, again, we are not talking about any practical problems. We are talking about problems which you are given as an intellectual challenge. And whenever we are talking about intellectual challenges, in many cases, people who invent the problems try to operate with integer numbers. So let's consider you have an equation which has integer coefficients, and maybe, just maybe, there is an integer root to this equation, integer solution to a polynomial equation. Now, it's worth to try. So if you have some equation, it's worth to try some integer solution. But where is this integer solution? Here's a very important thing. I just wiped it out, but the last equation which I had if you remember, that was it. So if there is a solution x equals p of the original equation, as you remember, then we can represent as a product of x minus p times some polynomial of n minus first degree, right? And now, since these are two polynomials, there is a constant a_n with it's a coefficient at x to the power of 0, if you wish. Now, what is here the coefficient which is actually a coefficient at x to the power of 0, the constant? Well, it's only if you have this constant minus p and this constant bn minus first, because everything else, all other members, contain x to some power greater than 0, first, second, etc. So only when you multiply these two members, you can get this. I'm sorry, this is n's. So that's actually how I derive this. It's only minus p times bn minus 1 is equal. So if there is an integer solution p to a polynomial equation with integer coefficients a, then this p must be one of those which are one of the divisors of a_n. So if you have this equation which contains only integer coefficients, look at the very last one, the free member of this equation, the constant, and look at the divisors of this particular number. Maybe one of those divisors with a plus or a minus sign can be the root. And, well, number of divisors is limited, obviously. For instance, if this is, I don't know, 12, then what do we have? We have 3, we have 2, we have 4, we have 6, and we have minus 2, 3, 4, 6. So there is a certain limited number of integers which are divisors of this constant. Try it. If it works, great. Because if you found one of them, then you can always represent your original equation in this format, and this will be an equation of a... Now, to solve this particular equation would be easier because it's a lower order equation. All right? So, if integer coefficients, and you're looking for integer solutions, look for them among divisors of the free member, the constant. which participates in the whole polynomial. Now, and the last one which I wanted to talk about is the following. We were just talking about if x equals p is a solution, then it can be represented in this way. Now, if this has a solution, if equations for b polynomial, if it has a solution, then it can be represented as a product of x minus q. Let's say x equals q is a solution. So it can be represented, and coefficients, let's say c, 0. Now x to the n minus 2, right? This is b. So we have lowered one more time the polynomial. So with every solution, we can represent original polynomial as a product of x minus p times x minus q times the c polynomial, which is of n minus second degree. And this in turn can be done many times. How many times? Well, apparently no more than n times. On each time we reduce the power, the degree of the polynomial by 1. So every time if we find the root, then we are reducing this remaining polynomial after these differences, linear differences, by 1. Which means that the polynomial of the nth degree cannot have more than n roots, because every new root found will reduce the power of this polynomial by 1. And we can only reduce it n times because our original polynomial is of the nth degree. Which means that polynomial of nth degree cannot have more than n different n solutions. Different is not really the right word, because sometimes you can have the same solution repeated twice. So n solutions. This is a very interesting observation, by the way. So quadratic equation cannot have more than 2 solutions, by the way. And linear equation cannot have more than 1. And the equation of the third degree cannot have more than 3 different roots. Can it have less? Well, that's a very interesting question. We know that there are no more than n solutions for polynomial of the nth degree. And I'm talking about complex numbers. In case of complex numbers, by the way, the quadratic equation always has some solutions, right? All right, so that actually is a subject of the next lecture, next theoretical material, not the problems which I will spend some time on in the next lectures or two. So there is something which is called fundamental theorem of algebra, which actually deals with existing of the solutions. I will definitely go into the details in that lecture, but right now we have already learned that we cannot have more than n solutions. The interesting is that the number of solutions always is equal to n, although some roots can repeat multiple times and should be counted multiple times. And this is actually the fundamental theorem of algebra, just formulated slightly different, but I'm definitely going to the details of this in the corresponding lecture. So just going a little bit ahead of myself, we have proven that there is no more than n solutions to a polynomial equation of the nth degree. But the fundamental theorem of algebra helps us to basically formulate that there are always exactly n solutions for the polynomial of the nth degree. It doesn't mean that we can find these solutions using some kind of a big formula, using some kind of multiplication, division, roots from the coefficients. No, generally speaking, we don't have it with polynomials of the fifth degree and more. But the existence of these n solutions is the fact. This is a theorem which is proven, which contains basically partially this fundamental theorem of algebra, which means that there is at least one solution, that's what it says actually, and this, that there is no more than n solutions. So the combination of these gives you really this interesting statement that the polynomial of the nth degree has exactly n solutions among the complex numbers. Well, that ends this particular lecture, and I encourage you to go through this material again, and don't forget the problem solving. I mean, we are making all this presentation for one and only one purpose. So you will learn how to solve different problems, and you will train your mind, your creativity, your analytical abilities, your logic, and your intelligence. So that's the purpose, and please register to unizor.com with your supervisor or a parent or a teacher and go through exams. Always welcome, and that's it for today. Thank you very much. Hi, I'm Zor. Welcome to Unizor Education. Continuing talking about high-order polynomial equations, I would like to demonstrate a couple of cases when you really can solve the equation of higher than 2 order. Just a couple of examples which I have here. What I do suggest you is, first of all, try to solve these equations yourself. They are in the notes on unizor.com website, notes for this lecture. So try to do it yourself. Whether you do or you don't, successful or unsuccessful, only then listen to this lecture. And it's basically about one particular technique how you can solve certain equations. There is no general formula for solving these higher order equations, as I was talking about in the lectures which precede these this particular exercise. So basically you have to think about particular case, about some peculiarity, about some technique maybe, or invent your own, whatever, to come up with a solution. So these are 3 examples of equations which have integer coefficients, and obvious attempt can be made to find integer solutions. So let me just try one after another. The first one is x cubed minus 7x plus 6 equals to 0. First of all, even without going into this technique which I'm going to use in all these examples, I actually can see something right up front, just looking at this particular equation. Now, what do I see? Well, here. 7x can be represented as minus x minus 6x plus 6. Now, why did I decide to do this? Lucky guess, if you want. But actually, I think I see, looking at this, I see that this is something which is the way to simplify the problem. Now, why I see it, I don't know. Maybe because of experience, maybe I solved probably hundreds of other equations which look like this one in some way or another, and at some points I basically came up with this particular technique. So first I'm looking and I'm trying to find out is there anything here which reminds me some way to ease the problem. And this is actually the way to do it, because obviously x can be factored out. So I have x squared minus 1. Now 6 can be factored out. And this is x minus 1 times x plus 1. As you know, x squared minus 1, difference of two squares is difference of the bases times sum of the bases. And what do I see now? I see that x minus 1 can be factored out from both places, leaving x plus 1 minus 6 equals to 0. So, obviously, I see there is a solution. X is equal to 1 of this original equation. Now, how about this? If this is equal to 1, this is also equals to 1. So, solutions to this equation is also this. So, x times x plus 1 equals to 6. This is where we are looking for solutions to this equation, where 6 is such a nice number that 2 times 3 would be equal to 6, right? So I already have another solution. X is equal to 2. And as you know, we have 3 different solutions for the equations of the third degree in the complex area, granted. So my question is, are there any other solutions? Well, obviously others are when this one of these is equal to minus 3 and another is equal to plus 3. So minus 3 times minus 2 also equals to 6. So x is equal to minus 3. As you see, I have practically guessed all the solutions of this equation. And it's not because I knew everything up front. Actually, I just kind of thought about x is equal to 1. It's kind of an obvious solution. But I didn't know about 2 and minus 3. All right, so let's check it out. 1 is 1 minus 7 plus 6 is correct. Now 2. 2 to the power of 3 is 8 minus 14. It's minus 6 plus 6, 0. Good. Minus 3. Minus 3 cubed is minus 27. This is plus 21, so it's minus 6, plus 6 is equal to 0. So all 3 are good. There are no more than 3 solutions, because this is an equation of the third degree. So basically I found everything. Now, this is not, I would say, a general approach. Well, there is no general approach, but this is a very peculiar solution which is based on some peculiarity of these numbers. So half of this I guessed, half of this I basically also guessed. I could have solved this quadratic equation as a quadratic equation. X squared plus x minus 6 is equal to 0. I can solve it using some formula. But again, I was using certain particular properties of these numbers and basically guessed it. So I wouldn't say this is a generalized approach, but what would be a generalized approach in this case? Well, probably the best way in this and the subsequent cases would be to look for integer solutions among divisors of the free member, the last one, the constant 6. So 6 has 1, 2, 3, 6, minus 1, minus 2, minus 3, and minus 6 solutions. So if we will check all these 8, some of them will fit, and we will find the 3 solutions, and then we can stop. So we can basically go and sequentially check. 1, does it work? Yes, works. 2, does it work? Yes, works. 3 would not work here, because this is 27 minus 21, 6 plus 6, 12. 6 obviously will not be as well. Minus 1 will not fit, minus 2 will not, minus 3 will fit, and the minus 6 will not. So that's how we can find all our 3 solutions. On the other hand, if we have found one, which is this, you know that you can always represent this particular equation as a product, equals product like x minus 1, because 1 is already found a solution, and some polynomial of the second degree. Second, because this is the third, this is the first degree, so we have to have second degree here, so the sum of exponents should be equal to 3. And obviously the first coefficient at x squared should be equal to 1, because otherwise this will not be equal to 1. I don't really need these parentheses. Right? So we need equal to 1, so this should be x squared plus 2, plus some kind of a something like this. And now we can basically find b and c by multiplying this and comparing with this. Well, let's do it. Now, x multiplied by this would be x squared plus x cubed plus bx squared plus cx. Minus 1 would be minus x squared minus bx minus c. And it's supposed to be equal to this, right? Now x cubed and x cubed is fine. Now x squared, there is no x squared here, which means b should be equal to 1. So bx squared minus x squared should be 0 because there is no x squared here. So b is equal to 1. Now cx minus bx should be minus 7, right? So b is equal to 1. So c must be equal to minus 6, right? So c is equal to minus 6. Then plus c would be plus 6, which corresponds to this, obviously, because 1 is the root of this polynomial, as we were already saying. So right now I can say that my original equation can be replaced with x minus 1 times x squared plus x minus 6 equals to 0. So obviously first solution is this, which we have already found, and the second solution is this, which we can actually use the formula if we don't want to guess. So this is what? 1 plus 24 divided by 2, right? So it's 5 plus 1 is 4 divided by 2, so it's x is equal to 2. And if it's minus 5, it's minus 6 minus 3. The same three solutions which I have kind of guessed before. So this is a little bit more scientific approach. Once you found one particular root of this polynomial, x is equal to 1, just by guessing, then use this to find the other two. Alright, fine. So let's remember both approaches. One a little bit less scientific, which I presented the first, where I was guessing lots of different things. Another is a little bit more scientific. Now, which one is better, by the way? Hard to say. I think that the element of guessing is very, very important. It actually is the result of your intuition, your mathematical intuition, which is basically the result of your experience. So there's nothing wrong with guessing. A little bit more, well, procedural approach, which is the second one. Well, first of all, it's still based on the guessing of the first particular root. And again, we kind of assumed that maybe there is an integer root, so we were just trying to check all the divisors. And we were lucky enough that on the first one we already got hit. But then everything else after that was relatively procedural, like presentation as a product of polynomial of the first degree and the second degree, etc., etc. So I wouldn't say that one is better than another. Try to be prepared for any kind of approach, whatever you need to solve the equation. It's your ingenuity. The whole exercise of solving these equations is to develop your creativity, your ingenuity, your analytics, your logic, whatever else. So that's fine if you guess it. That means that you have this math intuition. That's okay. Now, next one. X cubed minus 5x squared plus 9x minus 9 equals to 0. Well, again, I am kind of assuming that there are integer roots. So, integer roots must be plus or minus 1, plus or minus 3, plus or minus 9. These are all divisors of this particular equation. Well, let's do the same thing as I did before. Plus or minus 1, let's check them. That's easier, right? If it's 1, it means 1 minus 5, it's minus 4. This is 0, so that's not good. Minus 1, that's minus 1, and minus 5, and minus. Too many negatives. Not good, not 0. Let's try 3. 27 minus 3 squared is 9, 45. So 27 minus 45, that's what? Minus 18, right? Minus 18. Now, minus 18 plus 27, that's 9, and minus 9 is 0. Okay, so 3 is good, which means we can always represent this as x minus 3 times x squared plus bx plus c. Again, I'm using the coefficient 1 here because the product should have the coefficient 1 at x cubed. Alright, fine, that's easy. Now let's multiply this and find b and c. Right? That's easy. Actually, c I can find right now. Minus 3 times c, that's the only free member without any x, and it's supposed to be equal to minus 9, right? So minus 3 times c is equal to minus 9, so c is equal to 3. We got that. Alright? Now let's do the multiplication. X times this would be x cubed plus bx squared plus cx, but x is equal, so it's plus 3x, right? I'm using c is equal to 3 already. Now, minus 3x squared minus 3bx and minus 9. Again, I'm using c as 3. And this is supposed to be equal to x cubed minus 5x squared minus 9x minus 9. So, what can we do from here? Well, bx squared minus 3x squared, it's b minus 3, and it's supposed to be equal to minus 5. So b minus 3 is supposed to be equal to minus 5. So b is equal to minus 2. Now, how about this one? 3 and minus 2, that's 6, that's 9x. This is minus 9x, but no, something is wrong. What's wrong here? Minus 9. C is equal to 3. Right, something is wrong. This is 9. 3 times b, that's 6, that's 9. So why am I not... okay, let me check it. Let me check again. Is 3 the root? Okay, it's 27 minus 45, it's minus 18. Minus 18 plus 27, that's 9. Yes, 3 is the root. Okay, fine. Now, minus 3 times c should be equal to minus 9, that's correct. So x cubed plus bx squared plus cx, which is 3x, right? Minus 3x squared minus 3bx and minus 9. So x cubed is fine. B minus 3x is equal to minus 5, x squared, I mean. Right, so b is equal to minus 2. That's strange. How come it's not working? I'm supposed to have minus 9x. Oh, I'm sorry. This is plus, and this is plus. I have made this little mistake by writing the wrong thing here and then transferred it here. It's plus, of course, and minus 2 is correct. Alright. Well, as you see, I'm making some mistakes as well. Well, although this is just a very simple one. Alright, so basically we have found our equation. B equals minus 2 and C equals to 3. Which means we can rewrite the right part as x minus 3 times x squared minus 2x plus 3. Alright, fine. Now, is our life easier right now? Oh, absolutely. Because one solution we have already found, which is x is equal to 3. And another solution is to solve this one, right? And the roots of that thing is, well, it's obviously 1 plus minus square root of 1 minus whatever, 12 or something. Well, obviously this doesn't have any roots at all. Well, obviously it's seen from it's x minus 1 square plus 2, right? X minus 1 square is x squared minus 2x plus 1. So this is positive plus 2, I mean non-negative plus 2. So there are no solutions to this equation. It cannot be equal to 0. So in this particular case, in the realm of real numbers, we have only one solution. In the realm of complex numbers, we have 3 solutions. One from here and 2 complex one, real with real and imaginary part from here. And well, let's just do it. It's what? It's minus. It's 2 plus minus comma is 4 minus 4 12. So it's 1 plus minus 8 4 times 2 square root of 2 I. So that's 2 other solutions which are supposed to be solutions of the 3rd degree polynomial equation. I hope I didn't make a mistake here. Well, forgive me if I did. In any case, this is just a square. This is just a quadratic equation, so it's okay. Principle is more important than the details of this. And the last but not least, we have the equation of the 4th degree. X to the 4th plus 4x squared, no, x cubed, sorry. Minus 2x squared minus 12x plus 9 equals to 0. Alright. Now, this is, again, the polynomial equation of the 4th degree. And we are looking for integer solutions first, which means again we are looking among plus or minus 1, plus or minus 3, and plus or minus 9, which are divisors of the 9. Well, let's check it out. I mean, we don't have any better approach. Okay, start from 1. It's easier, right? So everything is basically x is equal to 1. So 1 plus 4 is 5, minus 2 is 3, minus 12, minus 9, and plus 9. Well, we're so lucky. 1 is the root. Okay, that's good, but that's basically not a complete path to solution, because 1 will allow you to reduce from the fourth to the third degree. All right? Okay, let's do that. So we have x minus... All right. We need something else. How about this? So we have x minus 1 times... Now the coefficient at x cubed should be 1, otherwise I will not get 1 when I multiply to get x to the fourth, plus, well, let's use bx squared plus cx plus d. Alright? So that is supposed to be equal to this. Since 1, x1, is a solution, it's supposed to be represented in this way. Alright, let's find out b, c, and d. Well, d is easier, right? Because multiplied by minus 1, it should give 9, which means d is equal to minus 9. Alright, fine. Let me make my job easier, and I will put minus 9 here. That's easier, right? Fine. Now we have only two variables. Let's think about x cubed. X cubed can be either minus 1, or when you multiply b times x, so it's plus b. So these are only members when I open the parentheses, which give you x to the third to the power of 3, right? Minus x cubed and plus bx cubed. Everything else will be lower degree, and I should get 4. So b is equal to 5, right? 5. b is equal to 5. And I will substitute it here because it's easier for me. Great. Now we have only one left, c. Alright, let's think about x squared. How can x squared be obtained? First of all, it's x times cx, which will be cx squared. And secondly, minus 1 times plus 5x, which is minus 5. So we have c minus 5, coefficient at x squared. It's supposed to be equal to minus 2. So c is equal to 3. C minus 5, so it's 3. Okay, the only thing which is left is the coefficient at 12 at x, minus 12. We have to check if we really have it. Well, indeed, x to the first degree can be obtained from x times minus 9, which is minus 9, and also minus 9 minus 1 times 3x, which is minus 3. So it's minus 12. So this is a correct representation. Fine. So we found one particular root, x is equal to 1, and we have reduced our equation to the third degree. So now we have to solve this. So let me get rid of this. It already played its role. And let's solve this equation. Found one root and reduced the power of the equation. Okay, what should we do with this one? Well, let's try again. What kind of roots this particular equation has? Again, we're looking for integers, right? So, minus 9, again. It's 9, so it's plus minus 1, plus minus 3, and plus minus 9. Well, let's try again. Let's start with 1 again. 1 plus 5, 6 plus 3, 6, 9, minus 9, 0. We are lucky again. X is equal to 1 is a solution. So we have another solution, x is equal to 1. It's a double root, if you wish. Yes, a particular solution can be represented twice in the polynomial, which means that this again can be divided into x minus 1 times x squared plus bx plus c. All right. Do exactly the same thing. First, we start from this free member. Minus 1 times c should be minus 9, so c should be equal to 9, right? 9. Okay. Now, so x cubed is fine, and minus 9 is fine. We have these two. Well, let's start from 5x squared. X squared can be either x times b, x, so we will have bx squared, or minus 1. And that should be equal to 5. So b is equal to 6. b is equal to 6. And all I have to do to check if I'm right, I have to verify that coefficient at x is what I'm really looking for. Well, coefficient at x is plus 3. Here, x can be multiplied by free member, which is 9x, or minus 1 can be multiplied by 6, which is minus 6. So 9x minus 6x is 3x, so that corresponds. Everything is fine, we didn't make any mistakes. So now, we have another root, which is x is equal to 1, and another equation to solve. Well, again, I'm guessing, but look, this is obviously x plus 3 squared, right? The x squared plus double x times 3, which is 6x, plus square of this. But, I mean, if you want to really solve it, use the formula or whatever else. Now, what does this mean? It means that, again, we have two roots. One root is equal to x equals to minus 3. And another root is also equal to x minus 3. So we have four roots, but these are actually two different values, each of them double. We have a 1 double root and minus 3 double root, and which is fine. Altogether we have four solutions to the equation of the fourth degree, which is correct, which is the way how it's supposed to be. These are all happen to be integer solutions. Fine. That's what it is. That's what it is. Okay. Basically, I think you understand the schema which I was using here. It's one of the approaches which you can use if you would like to solve some equation of the high degree. Try to find some root, and then using this representation as a product of x minus this root times polynomial of the lower degree, you basically make your life easier. Okay, there are some others, and I might actually present some other and further lectures. But this is it for today. Try to go through these solutions yourself again, and don't get scared if somebody offers you to solve the polynomial equation of a higher order, because most likely solutions are relatively simple. You just have to approach it properly, and if it's the problem given to you, most likely it has a relatively easy solution, not a generalized solution. There is no generalized solution in this particular case. Nobody would give you this problem. All right, that's it for today. Thank you very much. Hi, I'm Zor. Welcome to Unizor Education. I'd like to solve a couple of non-trivial equations. We all know how to solve some really simple things like linear or quadratic equations. And that's really not very interesting. Well, boring, quite frankly. You have the formula. If you remember it, it's good. If you don't remember it, it's kind of easy to derive it. And just use the formula. So as long as you have an equation with all its coefficients, just use this particular formula, you'll get the solution. So what if you don't have the formula? And excuse me. And in the real life, you don't really have the formulas all the time, right? So you have to invent something interesting, something new, something which will help you to solve a particular problem. And that's what actually the whole course of mathematics which I am offering here is about, to develop these qualities of creativity, logic, analytics, which will help you to solve something which you don't know how to solve before, and nobody taught you how to do this. So these are examples of this type of problems where you have to really think about it and use some non-trivial, non-standard methodology to come up with a solution. All right, let's go. Number 1, x squared minus 4x squared plus 7x minus 2 squared equals 16. Okay, obviously this is an equation of the 4th degree. X squared squared, right? So it will be x to the 4th. And obviously you don't know, nobody knows the formula, so we have to invent something peculiar for this particular case. And it does have certain peculiarity. And here is what I can suggest. You see, here is a very interesting thing. X squared minus 4x. What does it remind? Well, it reminds me x minus 2 squared, right? Because x minus 2 squared would be x squared minus 4x plus 4. So x minus 4x is part of something which well, it's my guess. I mean, maybe it's good, maybe it's not. But it looks like x minus 2. But this is x minus 2 squared. You see, this is exactly the peculiarity which you have noticed, or I have noticed. So let's just try to use it. Now, how can we use it? Well, there are many ways. For instance, if I will just open this up, I will have the same x squared minus 4x squared plus 7x squared minus 4x plus 4 equals 16. And now I see that these are common things. So I can just substitute y is equal to x squared minus 4x as a new variable. And now I have a quadratic, basically, equation of y. Now this is y squared. This is 7y plus 28, and there is a 16 here, so it's plus 12. And solutions to this are obviously minus 3 and minus 4, right? Because their product is the free member and their sum is this coefficient with a minus sign. But you can actually do it properly. It's minus 7 plus minus 49 minus 48. So it's minus 7 plus minus 1 divided by 2. Plus is minus 6. So it's minus 3 and minus 4. Yes, I was right. So minus 3 and minus 4. Okay, now knowing that, I can use this expression and basically find x. Now that's easy. So x squared minus 4x, this is minus 3, so it will be plus 3 equals to 0. That's one equation. And another is x squared minus 4x plus 4 is equal to 0. This is from minus 3, and this is from minus 4. Now, here I will have two roots which are
3 and 1. 1 minus 4, 3, 9, minus 12, minus 3 plus 3, correct. And here, this is actually x minus 2 squared, so x is equal to 2, and this is the double root. So these are my solutions. Now, this is actually double root, as I was saying, because it's x minus 2 squared. So I have 4 solutions, 2 of them are the same, which corresponds to the degree of this particular equation. It's the 4th degree, so it should have 4 solutions. And here they are. All right, now, the checking. Well, let's just do a quick checking, at least for something, like 3, for instance. 3 squared 9, minus 12 minus 3 squared 9. So this is 9. This is 3 minus 2, 1, so it's 7, 9 plus 7, 16, correct. And you can check the others, I'm sure they're good too. Okay, so what was an interesting part in this particular equation? It's just to notice that these two have something in common. That x minus 2 squared would look like this one plus some free coefficient. All right? So this is just a, it's a guess, if you wish. But the problem is that if you solve, I don't know, hundreds of problems like this, you would probably see these peculiarities, well, more or less easily. Okay, let's go on. X plus 2 over x plus 16 over x plus 7 equals 4. Well, it might look a little scary, and it's obviously non-linear, not quadratic, etc., etc. But there are 2 very important things to say about this. First of all, if we will just use the common denominator, which is x times x plus 7, now this would be x plus 2 times x plus 7, which is a polynomial of the 2nd degree. This would be x times x plus 16, also 2nd degree. And this would be x times x plus 7, x times x plus 7 times 4, which is also a polynomial of 2nd degree. So if we will just use this common denominator and put everything above it, we will have a quadratic equation on the top. And we can basically get rid of the denominator in this case. Now, there is one very important thing, and it's very important not only for this particular equation, but for many others. You see, all these non-trivial equations might have certain restrictions on the values of the solutions which we are looking for. Now, think about this. If I will really just do whatever I just said, which is just use the common denominator. So this would be from this plus this plus this equals, and divided by common denominator equals to 4 times x plus 7 times x divided by x plus 7. Now, my intention is just to get rid of this common denominator, because if these fractions are equal to each other and denominators are the same, then the numerators must be the same. And equalizing these numerators, I just have a quadratic equation, because this is x squared, this is x squared, and this is x squared. Now, but this is a very important thing. I said just get rid of the denominator and equalize the numerators. Yes, it can be done. However, existence of denominator right now, before I drop them, actually restricts certain values of the solution. X cannot be equal to 0, and x cannot be equal to minus 7. Because in both cases, this common denominator would be 0, and the whole thing would have no sense at all. Same thing if you will look at the original equation. It cannot be 0 here, and you cannot have 0 there. So x not equals to 0 and x not equals to minus 7 are initial restrictions on the solutions. So you have to really realize whenever you see something like this, which might really have certain restriction on the values of the solutions, you have to upfront do this and then look for solutions. Because during your looking for solutions, whenever you do this, you immediately lose this particular restriction. There is no restriction like this in this case, but in the original equation it was. So if by any chance I will get a solution to this quadratic equation, x equals to 0 or x equals to minus 7, I should really immediately discard it as the one which is outside of the domain of allowed solutions. I don't know whether I will or will not have these solutions among solutions of this quadratic equation, but if I will, I should discard them. So let's just solve this particular thing. That should be easy. So this is x squared, 2x and 7x and 9x plus 14 plus x squared plus 16x equals 4x squared plus 28x. This is my equation. So x squared, and 4x squared. So subtracting 2x squared from both sides, on the right I will have 2x squared. 9x, 16x, it's 25. This is 28, so I subtract 25 and I will have 28 minus 25, 3x. And finally the free member is 14, but it would be with a minus sign, right? Is this right? Okay, looks like it, I think. And solutions are divided by 2 minus 3 plus minus square root of 9 plus 4, 8, 8 times 14, it's 8 is 112, which is so x is equal to minus 3 plus minus 128, that's 11, so it's 11 over 2. So I will have x equals to 8. Oh, I'm sorry, it should be 4, not 2. It's a double first coefficient. It was 2x squared something, so it should be 4 here. So it should be 4 here, right? So it's 8 divided by 4, it's 2. And the next one is minus 14 over 4, so it's minus 7 seconds. Okay, so these are solutions, right? Now, none of them is this, so it's okay, no problem. They're not within the restricted set of solutions. So let's just check one of them. But 2 is easier, right? So 2 plus 2 is 4 divided by 2 is 2. This is 18 divided by 9. It's also 2. 2 plus 2, 4. Correct. And I'm sure minus 7 seconds also works fine. So what was interesting about this particular example? Well, the interesting thing is that although you can really very easily bring the equation to the square, to the quadratic equation, you should not forget that there is a denominator which you really have to be very careful about, and you have to really make some kind of exceptions. Your set of solutions is restricted to those which do not really put the denominator to 0. That's very important. Okay, the last one. X plus 1 to the minus second degree, x plus 2 to minus second equals 1.25. Okay. Well, let me rewrite it in a little bit better format. And one more thing, which I probably can really make my life a little bit easier. You see x plus 1 and x plus 2. I think it would be easier if I will use substitution. This would be 1 over x plus 1, and this would be square, and would be 1 over x plus 2 square. Now, it would be easier if instead of x plus 1 and x plus 2, I would make a substitution. Y is equal to x plus 1, and then x plus 2 would be y plus 1, right? Now, why is it easier? Because it's easier to deal with the denominator y than denominator x plus 1. So instead of this, I will use this substitution, and I will put here y and y plus 1, where y is equal to x plus 1. Okay? And what's equal to 1 and 1.25, let me deal with rational numbers, fractions like this. That would be easier. And obviously, I will try to do something similar to what I did before. I will get rid of the denominator, and I will put everything on the top to have some kind of a polynomial equation. Polynomial is easier than dealing with this thing. Obviously, I have to immediately restrict my set of allowed solutions to y not equals to 0 and y not equals to minus 1 to prevent these two denominators to be equal to 0. Now, after I have restricted myself this way, now let me just try to basically bring everything to the polynomial format. So I will bring everything to a common denominator, which is y squared times y plus 1 squared, right? I can always rewrite it using this, right? And same thing here. It looks a little bit easier, right? So the common denominator is y squared times y plus 1 squared. Now, what's good and what's bad about it? What's good is that on the left I will have quadratic, y plus 1 squared here and y squared there. But on the right, unfortunately, I have the polynomial of the fourth degree, right? So it will be y squared times y plus 1 squared. Well, whatever it is, let's just deal with this. So on the left I will have y plus 1 squared, and I will open it up, which is y squared plus 2y plus 1. And this would be y squared, 5/4 of y squared. So y squared times this, which is y squared, so it's y to the 4th plus 2y plus square, it will be to the cube, plus 1 times y squared, it will be y squared. That's on the right. Okay? Now, obviously, I have to put 4 here, so I will have only integer numbers. And what would I have? I have y squared plus y is 2y squared times 4, it's 8y squared plus 8y plus 4 on the left. On the right, I have 5y to the fourth plus 10y to the third, 5 times 2, plus 5y squared. I think that's right. Alright, so let's move everything on one side of the equation, and that would be 5y to the fourth plus 10y cubed. Now 5y squared, 8 on this side, so it would be minus 3y squared minus 8y minus 4 equals to 0. That's my equation. Equation of the fourth degree. Well, you don't like it, me neither. But let's just think about it this way. If I am trying to solve this particular equation, if I'm giving to my students, then and it has integer coefficients, then it does make sense to look for some solutions among integer numbers which are divisors of the free member. If you remember, when we're talking about equations of the higher order, it's always like this. If you have integer coefficients and you're looking for integer solutions, they must be among divisors of the free member, of the free element. Now, divisors are 1 and 2, basically. Well, forget about 1, probably. Let's just check 1. 5 plus 10, 15, minus 3, 12. Now, 1 actually does solve the problem. So 1 is a solution. Great. So if 1 is a solution, it means we immediately can divide it by 1. We have to extract the factor x minus 1 from this particular polynomial. So how can we do it? Well, very simply. It's 5y to the fourth minus 5y to the cube. If you will multiply, if you will factor out 5y cube, you will have y minus 1 left, right? Now, but we need 10. So minus 5, it means we have to add 15 y cube, right? Now, to again factor out y minus 1, we have to subtract 15 y squared. So this would be multiplication of factor of y minus 1 by something. This would be y minus 1 by something else. Now I need minus 3. I have minus 15. So I have to add minus 12 y squared. Right? 5 minus plus 15 minus 15, no, plus 12, I'm sorry, plus 12. Minus 15 plus 12, that gives me minus 3. Now, if I have plus 12, I have to have minus 12y to have y minus 1 from here. But I have minus 8, so I have to add 4y and minus 4. As you see, here is, I have rewritten my equation by adding and subtracting certain things to every member, so that on in each pair of parentheses I have 1 minus y minus 1 as a factor. All right. Now, why did I do it? Because again, my divisor of 4, which is 1, fits as a solution. I basically guessed a solution, but since I have guessed a solution, I can factor out y minus 1. If 1 is a solution, I can factor out from the polynomial 1 minus 1. And how to do it? By basically breaking each component into something which I can factor out y minus 1. So in this case, it would be y minus 1 times 5y to the third. Okay? Now, in this case, it would be plus 15 y squared. In this case, it will be 12y. And in this case, it will be 4. So that's my equation. This is the same as this one. Since I have guessed my first solution x minus 1, y minus 1, I can separately have y is equal to 1 as a solution, and by the way, it's allowed solution because it's not 0 and it's not minus 1, after which I can solve this equation. Because when the product of two polynomials can be equal to 0, but either one is equal to 0, and that gives me this solution, or this is equal to 0. Now I have to find some other solution. Well, let's try to guess again. 1 we have already exhausted. 1 is definitely no more than a root, so it's not like a double root. How about minus 1? Well, let's check it out. This would be minus 5 plus 15, that's 10. This would be minus 12, which is minus 2, plus 4, 2. So minus 1 doesn't really fit. Now let's check 2. Well, 2 obviously will not fit because everything is positive, but how about minus 2? Minus 2 cubed would minus 8 times 5 is minus 40. Okay, so this is minus 40. Let's write it down. Now this is, if it's minus 2 squared, it's 4. It's times 15, it's 60. This is minus 2, it's minus 24. And this is plus 4. Minus 64 minus... Okay, so minus 2 does actually fit. Great. If y equals to minus 2 fits, it means I can represent it as y plus 2, right, times something. So let's check what y plus 2 might be. Well, if this is supposed to be broken down, so I will have y plus 2, it should be 5y cubed plus 10y squared, right? Then it would be 5y squared would be factored out, and what will be remaining is y plus 2. Okay, now I have 15y squared. I have 10 here, so I have to add 5. Now, so this is factorable by y plus 1. Now, here I need 10y. So if I will factor out 5y from both, I will have remaining y plus 2 as well. Great. Now, I have 10, I need 12 plus 2, y plus 4. And this can be factored out 2, and I will also have y plus 1. Y plus 2, sorry. So, right now I can rewrite this as a plus 5. A plus 2 times. In this case, it's 5y squared, right? 5y squared. In this case, it's 5y. And in this case, it's 2. So this is my next representation of the same equation of the third now power as a product of 2. The first power and the second power. Okay, now from this I see that my new solution is also good because it's not part of the prohibiting values for the denominator. And what's left, so if the product is equal to 0, either this is equal to 0, and that gives me the solution minus 2, or this is equal to 0. So this is my, this time, a quadratic equation, which I already know how to solve. This is just the formula, which we all remember. However, it does not really have any real solution because 5 squared minus 4 times 5 times 2 is less than 0, so we don't have any solutions in this case. So, this is the end of it. I've got two solutions, so it's a quadratic equation. It's a fourth degree equation which can be represented as quadratic equation and two multipliers. So one would be y minus 1, another is y plus 2, and another is 5y squared plus 5y plus 2. This has no solutions. This gives me 1, and this gives me minus 2. Both are allowed. Well, let's just check the solution for x. Now, we know that x is related to y with this formula. So y is x plus 1, so x is equal to y minus 1, which is either 0 or minus 3. Okay, 0. Well, this is 1, and this is 1/4, and that gives me 1.25. So 0 is really the solution. We just checked it out. That's fine. And minus 3. So this would be 1 over minus 2 squared, which is 1/4. And this would be, if it's minus 3, then it's minus 1 squared 1, so it's again 1 and 1/4, so it's 1.25. So yes, checking fits fine. So this is a solution, both solutions, and that's the end of the this particular equation. Equation seems to be a little bit complicated, and again it's transferred into x to the 4th degree polynomial, which is, pretty difficult thing to solve. However, with certain degree of ingenuity and creativity, we have really decided to look for integer solutions, and we found them. Obviously, if, again, let me just repeat it, if I'm giving this particular problem to students to solve, then I kind of specifically chose not just a general equation of the 4th degree, but the equation which can be solved in some reasonable way. So to look for integer solutions is a reasonable way which I have decided. Okay, so that's it for this particular lecture. The purpose was to introduce you to some non-trivial examples of equations to solve. And I'm sure as the time allows, I will probably introduce more and more problems of this type. The number of available problems of this particular kind, like non-trivial equations to solve, is really unlimited. And the more time you spend to basically solve these non-trivial problems, non-trivial equations, well, the better your creativity and your logic actually will be developed. So I do recommend you to solve as many as possible non-trivial examples when there is no ready-to-use recipe, when you have to really invent something, you have to guess something, and that's what's very important. Okay, thank you very much. As usual, you can find all the information on my website and notes for this lecture. Thanks again. Until next time.